All right, so I was going to get into acids and bases real quick. So the Arrhenius theory of acids and bases really works well for you as something of it's a model of what they are. It's not going to work for everything, but it works very well for many situations in acids and bases, and certainly will get you through high school. Um, he said, by the way, being the Swedish scientist, he was one of the first people to figure out that global warming was going to be a problem. And look where he lived many, many years ago, 100 plus years ago. And he figured out that carbon dioxide was going to be an issue with temperature on the surface of the planet. But anyway, here we go. So he said that acids will produce H plus in water. So a famous acid, hydrochloric acid, when you put it in water, it separates into an H plus and a Cl minus. And he said a base would produce OH minus in water. So a famous base, sodium hydroxide, would become sodium plus and OH minus in water. So here, sodium hydroxide produces OH minus, HCl produces H plus. That's what he sort of said an acid would do. It would make H plus, and a base would do, it would make OH minus. So why is this significant? Why do you need to know this for biology and chemistry and whatnot? Well, actually, first, before we get into that, I will call H plus a proton. I will use those terms interchangeably. And that is because if we think about what H is, what a hydrogen atom is, it's a proton in the nucleus and an electron flying around. And if we wanted it to be H plus, what do we have to do? We can't mess with protons. One proton is what makes hydrogen hydrogen. If we add another proton, it would be helium. So we're not going to do that. We're going to take an electron away. And taking an electron away would leave us with just a proton. So H plus is the same as a proton. It's one proton, that's why it's hydrogen. There's no electrons, so it has a positive charge. So H plus is a proton. All right. Why is this significant? When you have acids and bases and you react them, they form water. And I told you there's actually, for much more braver chemists than I, you can take very concentrated base and show people how you take some of that base and unclog a drain or dissolve what you need to dissolve to do that. Or you can take very strong acid and corrode something in the acid, and then you mix them perfectly ratio and you'll make water and you can drink it. So even though you had something that could clean a drain and something that could dissolve, you know, metal or what, not dissolve metal, but, corrode the heck out of something there. You can mix them and form something as harmless as water. So acids and bases combine to form water. In most cases, won't be true with Lewis, but I don't think we're going to get into Lewis. So notice here that when we did all this, we had the sodium and we had the chloride ions, and we didn't really talk about them, right? The hydrogen made H plus, and that reacted with the base, the OH minus, and formed water. But we didn't talk about the sodium. We didn't talk about the chlorine. And what we call those is spectator ions. So anything that's really not involved in what we're talking about and sort of swims around in solution before and afterward, we call those spectator ions. And much to your begruntlement, I called Perry the platypus, because Phineas and Ferb always say he's a platypus. He doesn't do much. And you all yelled at me that he's a spy and whatnot. And I was just trying to get you to think that spectator ions, they don't do much. So anyway, all right. But that's what they do. Spectator ions just sort of sit there and watch what's happening between the hydrogen and the hydroxide in this case. All right, so acids. The typical formula for an acid is HA. You're going to have that leading H. Unlike molecules where H will sort of be more in the mix of things, the CH4 or C2H6O2, right? H is sort of in the mix of things. H is going to be front of the formula because it acts like a metal in this case. We've always said that H sort of has a foot in the group 1A metals and also a foot in the non-metal side of things, should be next to helium above fluorine, because it kind of acts like both of those things. Well, it's acids where it acts like a metal. It comes off as a positive cation like metals would, like sodium would if it were with Cl. So, or lithium or any of the other group 1 metals. So you have a leading H. The anion's charge will dictate how many hydrogens you need. So hydrochloric acid, Cl is Cl minus based on where it is on the periodic table. It's one away from a noble gas. So hydrogen, you only need one H plus to balance that charge. Hydrobromic acid, bromine's a halogen as well, so you only need one. Sulfuric acid, the sulfate anion has a -2 charge, so you need 2 plus 2s to balance that out. So it's H2SO4 for sulfuric acid. Phosphoric acid, PO4, is a 3 minus anion, so you'll need 3 H pluses to balance that out. These in red you should really know for the test: hydrochloric acid, sulfuric acid, phosphoric acid, acetic acid. They always have a leading H. As you can see, the H is always the first thing listed when we make the compound. And anyway, acetate anion is -1, so you only need one H plus to make that happen. But here you can see it has hydrogens in the acetate form, and that's why they're not leading in that case. They come after the carbon. Anyway, these are weak acids. Acetic acid is vinegar. You know it's a weak acid because you can eat it and it doesn't kill you. Citric acid, which is in drinks and whatnot, drink mixes, you know you can drink that without killing yourself. Ascorbic acid, vitamin C, you know you can eat that without killing yourself. Formic acid is another weak acid. It's what ants produce. They actually will bite you and then spray formic acid in the bite. That is not true with our local fire ants. They actually inject a venom, which is a base. It's an amine that they inject in you. So that is not what fire ants do, but any other ant that bites and hurts will spray formic acid on you after it bites you so that you really feel it. All right, so those are the acids. So the acid's general formula will be HA, leading hydrogen because it's producing H plus, according to Arrhenius. And now bases have the typical formula metal OH. We're talking hydroxide anions, OH minus, so whatever metal it is that they're grouped with, and the OH minus. Group 1 and Group 2 metals make great strong bases. So sodium hydroxide, that's a Group 1 metal, +1 charge. It only needs one OH minus to balance. So sodium hydroxide is NaOH. Calcium hydroxide, calcium's a Group 2 metal. It would need two OH minuses to counteract its +2 charge, so it's calcium OH2. So barium hydroxide, barium being a Group 2, would be BaOH2. Potassium hydroxide, potassium being Group 1, would be KOH. Those are all strong bases. So strong bases will typically have the formula MOH. Now there's weak bases as well. They are amines of the form of some nitrogen with 3 things connected to it. I put an X here for general. Ammonia is kind of an example of that. You have nitrogen connected to 3 hydrogens. Triethylamine is a famous base. It's a famous base. It's a famous weak base, or at least one that you might hear of if you go on in chemistry. So that has 3 ethyl groups connected to it. Ammonium hydroxide, NH4OH, is another weak base. It's basically what happens when you put ammonia in water. You get the H from the water going with the ammonium ion and the OH that's left sticking around. So you can see the difference between NH3 and NH4OH is water, H2O. All right, so those are the bases. And as sort of practice, I asked you to identify each of these as whether it was a base or an acid. So sodium hydroxide, NaOH, does not have a leading H, has an OH anion, so that's going to be a base. H2SO3 has hydrogen as a leading, so that's going to be an acid. NHC5H10, I believe that's piperidine or something, I think. Anyway, the point is it has the N in front, so that's going to be a weak base. This is ammonia, that's a weak base. Calcium hydroxide has EOH, that's a base. Lithium hydroxide has EOH, that's a base. H3PO4, phosphoric acid, has a leading hydrogen, so that's an acid. HCN, that's cyanic acid. Anyway, has a leading H, so that's acidic. NH4OH, that's the ammonium hydroxide, that's a base. And HC2H, that's acetic acid, that's an acid. All right. So we talked strong and weak up here, and what's the difference between strong and weak? Well, if you think of a pacifier here as the H plus that these 2 acids are trying to give away, Maggie here would be a strong acid. It's very easy to get that H plus from her. She'll give it to you in a heartbeat. This baby here, on the other hand, even though it does have that H plus, it's not going to give it to you that easily. That is a weak acid. You can get it from it. It's just not as frequent as you can from a strong acid. So that's the image that I present to you as the difference between a strong acid and a weak acid. But that also goes back to equilibrium. Strong acids have very much a one-way equilibrium, and that is with the products. So the HCl will produce H plus and Cl minus almost completely exclusively, so it's all H plus, whereas a weak acid like acetic acid, does more of that back and forth. So here's the H is connected as part of the molecule, can't do the damage that H pluses do, and here the H plus is separated, but it goes back and forth. And a nice thing for that, actually, before we got into that, we got into this FET, but before we get into a visual for that again, Bronsted Lowry sort of jumped on to the Arrhenius definition, and they said there's no way H plus exists in water because it's a proton. It's a supercharged little molecule particle thing. It's not going to just hang out by itself. It's going to glom onto water and be H3O plus. And there's some truth to that. If you have an H plus in water, you may remember lone pair of electrons are going to have a negative charge. And if you have a little positive charge that's just free to move around, it's not going to just sit by itself. It will sort of hover around that. It'll be attracted to and hover around those minus electrons, and as a result form this H3O plus. So Bronsted Lowry said acids were proton donors, something that had a hydrogen to give up, and in water that would be H3O plus. So in the simulation I'm about to show you, whenever you see H3O plus, that's the same as that H plus. It's an acid being formed, but that H plus wouldn't exist by itself. It's going to exist connected to the water. And a base, they said, is a proton acceptor. So here's this amine. It has this lone pair available to that proton. If there's a proton swimming around that wants to find it, it can find it. And so bases like amines are proton acceptors. All right, so now let's go to this real quick. I know I'm boring you. Where do I want to be? I want to be here. Nope. I want to be here. I want to be here. All right, so here is the FET we did. So here's water. As you can see, water has some just spontaneously, some water will get together and form H3O plus. So it'll form a little bit of the acid and a little bit of the base. So as a result of the fact that they're always going to be equal in number, the pH of water is 7. And we were doing this to sort of monkey around with pHs. If you put a strong acid in this solution, so the strong acid being this HA, and we look in this magnifying glass, you can see there is no gray HA in there. It all went, it's a one-way reaction, one-way equilibrium to this H3O plus. There's a whole bunch of H3O plus in there and a whole bunch of whatever the anion is minus. So if this was hydrochloric acid, that would be Cl minus. If this was sulfuric acid, that would be the SO4 2 minus or thereabouts. So that's a strong acid. You can see the pH is very low for a strong acid. This is a cool thing where you can dip in your pH paper and compare the color to whatever it is. All right, so then there's weak acids. And weak acids, as we talked about, are in this equilibrium situation where they're not so sure they want to get rid of their H+. So here's HA, so this is like acetic acid, and it wants to hold on to its H+, not give it up as much to the solution. And if we check this pH, you can see it's much different. It's like 5, and if we go back to the meter, it's 4.5. You can get something more specific like that. And then there's a strong base. So a strong base is the same situation as the acid, only now it's giving up that OH minus instead of the H plus. So that OH minus is swimming around. You can see no MOH available. None of the green species are there. But in the weak base, you will see a lot of that gray, not green, gray. A lot of that gray species, a lot of that that gray stuff exists in a weak base because it's not all sure it wants to take the proton off of water to give it OH minus. So the pH difference between a strong base of 12 and a weak base of 9 is a fact of matter of how much of that OH is being released. Strong bases will release a bunch of that OH and bring the pH way up. Weak bases aren't so sure they want to form that. It's an equilibrium back and forth. And so that's why that's that way. So I do highly recommend this FET. This is the acid-base solutions FET, which you can find on my webpage. And I'm going to stop sharing here because I'm sure I've bored you to death.